This is problem number 11. And I've written out our timeline and then pertinent information from the problem, as well as the formulas we're going to need are over here on the left. So Mike buys a perpetuity immediate with varying annual payments, and it looks like this. The first 5 payments are worth 10. We're just going to go with dollars. So we have $10 payments for the first 5, and then those $10 payments are increased by some percentage k. And I've cheated this a little bit. Instead of saying 1 plus k, I'm just multiplying by k. And then we've got our present value factors underneath here, right? It's perpetuity immediate. Payments happen at the end of the year. So this payment is discounted back once. This one discounted back twice. Here discounted back 3 times, and so on and so forth. So this first chunk of steady payments of 10, I think is pretty straightforward. That is just an annuity immediate of 5 years with an interest rate of 0.092. This second chunk is going to take a little bit more work. So I'm going to write out this series of payments. We have 10 times k times v to the 6th plus 10 times k squared times v to the 7th plus 10 times k to the 3rd v to the 8th, and that's going to go on in perpetuity. So it's infinite, it's geometrically increasing, but it doesn't have an endpoint. So we're going to use this little formula right here, which gives us the sum of an infinite geometric series. We just need to find the common ratio. So let's factor out what we can from each term, and that's going to be 10 times k v to the 6th. So this first term is going to serve as our factor because it's shared by every term in the series. So what's left? Well, here it's just times 1, and here we have a k times v left, and here a k times v, or a k squared times v squared, and then a k to the 3rd times v to the 3rd, and so on and so forth. So our common ratio is kv, our first term is a, so that means we can rewrite the second piece of the perpetuity as such. And this here, I'm going to go ahead and translate this into this formula here. So that is 1 minus our present value factor raised to the 5th over our interest rate. And then we're told that all of this has a present value of 167.5. From here on, it's just algebra. So we've kind of got 3 forms of the problem here. We've got the scenario in timeline form, and then maybe in series form or annuity form, and then we get down to algebraic form where we can do our work and solve for our unknown. So first things first, this right here is going to resolve to a singular constant of about 38.7. I'm just using my TI calculator here. You can, of course, use the financial calculator as well. But either way, this is the value you should get. And then this one is going to take a bit more work because we have that k in there. So I'm actually going to leave that somewhat alone for the moment. Equals 167.5. But we're going to subtract, right? We can just subtract this 38.7 from both sides. So let's go ahead and do that. And instead of 167.5, we are going to end up with 128.8. So continuing with the algebra, I'm going to multiply both sides by 1 minus kv. So that will give us, and I'll distribute at the same time as well. So multiply u by u to get this value here. Then we get our unknowns all together on the same side. So I'm going to add 128.8k kV to both sides, and we are zeroing in on the final answer. Factor out the unknown. So that leaves k times 10v to the 6th plus 128.8 v equals 128.8. So to get k, we're just going to divide both sides by this term here, but this term has a constant value as well. So let's go ahead and run that through the calculator. You get just about 123.8. So I'm going to round it. So we could simplify this term, and this left side, we'd have 123.8k equals 128.8. Divide both sides by 123.8, and you get something that is pretty close to 1.04. But remember, I cheated it just a little bit at the beginning, letting k be 1 plus k and not just the interest rate. So the answer we actually want here is 4%, but I think that's fairly obvious. So we would select A and move on. So just a quick review. Half of the battle is writing out your timeline and looking at your payment structures, and then you convert that down either to annuity symbols or annuity formulas or a series that you can condense down into a more singular formula. And then from there on, it really is just algebra.